Honors Math 2, Unit 4. This is first period in the year 2019. Right before 2020, when everything becomes clear. 2020, for those of you who aren't paying attention, okay? All right. So once again, I felt like I needed to create a light overview of the whole chapter in case you have forgotten things from Unit 4. I can lightly overview what Unit 4 was about before you start the problems. Or if you are doing the problems, just to kind of gloss over, oh yeah, this stuff is what were the main ideas, what did we learn? And remember, if you need a specific video from 4.1 or 2 or 3 or 4 or 6 or 0 or 5, they are on my website. I have the full library there. So what was Chapter 4 about? Chapter 4 was about triangles. And what happens when you do certain things to triangles. And the first one was, what happens when you connect a midpoint from one side of a triangle to a midpoint on the other side? That created something. That created something called a midsegment. Midsegments had two very specific properties about them. The properties were, they were parallel, and they were also half the length of the side it's parallel to. Meaning this middle piece, this midsegment, if you doubled it, it would be equal to the bottom. They are not the same as each other. This is half of that distance of the side it is parallel to. A triangle midsegment was the first concept in Unit 4. We had a variety of problems that you had to do where you had to double the midsegment to equal the side it was parallel to. And then, of course, you could not get that confused with something called a median. I'm going to jump to number 4. A median wasn't from, a midsegment was from a midpoint to a midpoint, but a median was different. It was something that went from a vertex to a midpoint. If I'm going from the corner, that's what a vertex is called, and I'm going to a midpoint on the opposite side, that is called a median. Medians, when you had all three medians and they intersected, all three medians would intersect in a point called the centroid. And so everything else in Chapter 4 beside that midsegment was about how can we create these 4 specific points in a triangle. What were they called? What were they made up of? And our big idea came in Chapter 4, where we had to know how the circumcenter and the incenter and the centroid and the orthocenter were created. What were they created by inside a triangle? And 3 of those had very specific properties about them that you had to know. So let's go back to Section 2. In Section 2, we learned about perpendicular bisectors and how if something was on the perpendicular bisector, it was equidistant to the endpoints. And it didn't matter where you were on the perpendicular bisector, it was still going to be equidistant to those endpoints. Which is why, if you had perpendicular bisectors of a triangle, oh, it doesn't even have it there. I thought it was here, but it's not. The problems that we did with perpendicular bisectors were setting these two distances equal to each other. Because they were equidistant on the perpendicular bisector to the endpoints. And that also let us know that if we had an isosceles triangle, that the point P is on the perpendicular bisector. We kind of had to figure that one out as well. There was something called angle bisectors as well. Angle bisectors of a triangle created something called the incenter. That's where I thought the circumcenter and the incenter was on this section, but apparently it is not. It must be in Section 3. Here it is. when you take the perpendicular bisector of each side of the triangle, perpendicular bisectors, since they are equidistant to the endpoints, that makes point AP the same distance as PB is the same distance as PC. Those distances are all the same. That means that you could technically draw a circle through all three vertices because they're the same distance apart from that circumcenter. Angle bisectors would create something different. Angle bisectors are equidistant from the sides of the angles as long as that distance is measured at a perpendicular angle, which this one does. So therefore, angle bisectors, where they intersect, is a point called the incenter. Incenters are equidistant to the sides of the triangle and the sides of the angle, meaning that if I wanted to, I could fit a circle that would perfectly touch all three sides. And by the time we got to section 4, we had to know that perpendicular bisectors created the circumcenter of a triangle, angle bisectors created the incenter of a triangle, the medians of a triangle created something called the centroid, and then the altitudes of a triangle created something called the orthocenter. If I didn't mention it, an altitude was the last thing I talked about. It is the side that is perpendicular to the line containing the opposite side that goes through the vertex. And so, sometimes your altitude is on the triangle if it's a right triangle. Sometimes the altitude, it goes through the middle. That's the circumcenter. These are altitudes because they go through the vertex and are perpendicular, but they don't necessarily bisect. If it's an obtuse triangle, sometimes you have to extend the line out a little bit to go perpendicular to the line containing this side. And then, of course, the orthocenter would be way outside of the object if you're dealing with altitudes of an obtuse triangle. We did talk about constructions. You had to learn constructions as a part of this unit. For your final, I might as well say this for the group. There's no way that I'm going to have you make a construction on your final because your final is all 100% multiple choice. Because of that, do not expect me to give you a compass and a straight edge because you're not going to need one. But you might have to be able to know what would produce a median or an altitude or think of the multiple choice questions that I asked you. Do you know how? And I'm not talking a lot because that's not the main idea of this whole chapter. There might only be one question. But do not think that constructions are a main idea because they're not. Really, it's do you know these parts? Do you know how to solve problems involving those things? The last idea, which there are going to be some questions on, will deal with inequalities, and there's several ways you can do it. The first big idea is that the largest angle is across from the largest side, and the smallest angle is across from the smallest side. As angles get bigger, think about the side across from it, how they get longer every time you open up the angle. We also talked about how you can tell whether you can make a triangle or you cannot make a triangle. And whether you remember that if you had a 2, a 3, and a 7, you can't make a triangle from that because the two smaller sides, when you add them together, needs to be greater than that third side. That was called the triangle inequality theorem. And so we use inequalities to know what the longest side is and the shortest side. We also use inequalities to tell if we could make a triangle. We could even figure out what the range of possible values would be for the third side of a triangle using inequalities. That's just merely putting the difference of the two numbers on the left-hand side and the sum of the two numbers on the right-hand side and saying your x value is in between the difference and the sum. Of course, we compared the smallest and the overall. I don't remember if we had a lot of these on the final, but when you had to compare two triangles together, don't just go off of the smallest angle. I remember this being a commonly missed question, not a 50%, but like in the 30% range who missed questions like this. Sometimes you're looking and this is the smallest angle and you go, what's across from it? This must be the smallest side. Well, not necessarily. But when you have two triangles, use both triangles to figure it out. 30, yes, is the smallest angle, so across from it, yes, QR is the smallest one of the left triangle. But since the right triangle has a 40 and a 50 degree angle, 50 is bigger than the 40, meaning QR is bigger than the RS. So that must mean that RS is the shortest in this diagram, even though it's across from a 40 degree angle as compared to the 30 degree angle. This triangle on the right hand side compares both. And that's what I recommended you figured out. Highlight which angle has or compares both triangles. The last thing we talked about where it was mid-segments and using the slope formula, using the midpoint formula, using distance formulas. Those will be an idea as we get through Unit 5. It'll show up some more. But really this chapter is about triangles and what happens when you have perpendicular bisectors, angle bisectors, altitudes, and medians. Throw in some mid-segments, throw in some inequalities, and that's Unit 4. That's where I'm going to end.